Hello everyone, this is Professor Kuehn and welcome back to my lectures on electricity, magnetism, and light, where we have been looking at the work of John Tyndall. We've been looking at his lectures on light, and we're in chapter 23 in A Student's Guide to the Great Physics Texts, volume 3. This is the chapter on crystal symmetry and light rotation. In our last lecture, what I did is I talked quite a bit about his sections 23.2.2, where he talks about the colors of films of selenite in polarized light, and the colors of crystals in polarized light explained by the undulatory or the wave theory. Remember there what we're talking about is how if you take crossed polarizing filters and you pass initially unpolarized light through these filters, because they're crossed, it will be dark. But if you place a piece of birefringent material between them, you can allow light through them, because in a sense the birefringent crystal repolarizes light. It rotates the plane of polarization. And if you use a very thin layer of birefringent material, like a thin sheet of mica or a thin sheet of cellophane tape, then you can make it so that it rotates a particular color by the correct amount to make it through the second polarizer so that it will appear colored. So that's where you get these beautiful colors of thin sheets of mica or thin sheets of cellophane tape. That brought us about up to page 276. Now, in the rest of this chapter, what Tyndall does is goes through a number of different experiments that he carried out that sounds like it would have been fascinating to listen to this lecture, where he does various experiments in front of a crowd. And it's going to be hard to go through in great detail all of the experiments that he does. So I'd encourage you to read through these. You'll understand some of it, you may not understand other parts of it, but I just like to highlight some of the kinds of things that he does. So one of the things that he talks about is the colors that are produced by strain and pressure. Again, this is something that you did in lab this past week, where you took cross-polarizing filters and you put plexiglass between them, and it was dark because the polarizers were crossed, but then you squeezed the plexiglass and you saw that in certain regions of the plexiglass, suddenly you could see light making its way through. What does this imply? Well, based on our analysis in the last lecture, it implies that the plexiglass, where it is under strain, becomes birefringent so that it is able to rotate the plane of polarization of light. That's exactly what he sees. He takes a piece of glass, and this is shown on figure 277. I believe this is the section where he talks about this. He takes a piece of glass, puts it between crossed polarizers, and then bends it a bit. And when you bend it a bit, then certain parts of the glass become compressed and other parts become expanded. And when you have the molecules of the glass compressed, you basically introduce this birefringence, because you introduce an asymmetry in the crystal, which means that lights that are striking it with different polarizations will travel at different speeds because there are different refractive indices, which arise from the different stiffnesses of the crystal and different orientations. So as a result, you see sort of this birefringence that is introduced in areas that are under stress, either under compression or expansion. So the interesting thing here is it allows one to determine if certain regions of plexiglass or glass are under stress or strain. So that's one thing that he does. He does another thing that's quite interesting, which this would be a really fun experiment to do in the laboratory. This is depicted in figure 23.6, where he takes a source of light, and I guess that is, I can't read the letter there, but there's this big box that's a source of light, and then he has some polarizing filter at position B. So you have polarized light striking this piece of glass that is denoted by S over to S prime. It's a thin sheet of glass, and then another polarizing filter at location, I believe it's N. So you have cross polarizers, and then what he does is he rubs a piece of, he says, damp wool across the glass, and it causes the glass to vibrate. That is, sound vibrations are set up in the glass. It's a bit like if you were to lick your finger and rub your finger around the rim of a wine glass. If you do that just right, it begins to hum. Well, similarly, if you rub this piece of damp wool across the glass, it begins to hum. And what that means is that the glass is vibrating. And the vibrations, if you think about what sound is, it consists of compressions and expansions of a medium through which it travels. So the glass is being compressed in some locations and expanded in other locations. And so because of compression and expansion lead to birefringence, one can then see, using these cross polarizers, the regions that become compressed or expanded. So this sounds like a fascinating experiment that he carries out. He also does some experiments with glass, unannealed glass. So just some terminology here. If you take a material that is very warm and you suddenly cool it, that's called quenching it, and you kind of freeze in any kind of disorder that's in it. And if you anneal it, then that's when you cool it down very slowly, and it gives it kind of a time to work out any stresses or strains, so it becomes very uniform. So if it is unannealed glass, it means it's more like it's quenched, and so there might be some inhomogeneities that are kind of frozen into it. And so when you look at this through cross polarizers, you can see regions that the stresses and strains are frozen into the glass. He also does some experiments where he heats up regions of glass, and when you heat it up, there are non-uniformities in it, and because of these non-uniformities, there are regions that are under stress or strain, and as a result, they become birefringent, and it has the same kind of effect that he's been talking about. So you see kind of a common theme in this, where he's using the polarization of light to probe the structure of solid materials. Let me jump ahead to, he talks about some experiments, and I think this is a challenging section, page 281, where he illustrates that blue and yellow are complementary colors. And I don't want to spend a lot of time on this because I don't think he refers to some earlier sections in his lectures on light that we haven't read, so I think we don't have some of the background that's necessary to get a deep understanding of this. But let me just say that if you were to take blue and yellow pigments like paint and mix them together, you get green. But if you take blue and yellow light and you overlap them, you get white. And that's because blue and yellow are complementary colors. So maybe I could do another lecture at some point on color theory, but that's an important point that he brings out in this section. Section number 23.2.8 is on the magnetization of light, and I want to say a few things about this. This is a fascinating experiment that Tyndall is relaying to us, and he's talking about an experiment that was originally done by Michael Faraday. Now, next week, we're going to talk in some length about the work of Michael Faraday. He was a scientist who lived and worked in England. He was, I think, a Scottish scientist. But he is probably one of the most pivotal and important figures in the theory of electricity and magnetism in the 18th century, if not in history, because he did some very careful, a huge number of very careful experiments that clarified the relationship between electricity and magnetism and finally light. And what Tyndall is doing in this section is talking about a small subset of Faraday's experiments where he explored the relationship between polarization of light and magnetic fields. So if you look at the diagram on page 283, he illustrates Faraday's setup. So you have a source of light at location N, and I forget what some of these other things are, but one of the main points is that he has a polarizing filter. I think it's H. I guess I have to look at the text in detail, but he produces polarized light, and then this light passes through a material that is strongly magnetized at location M. You see some wires hooked up to an electromagnet, and the electromagnet magnetizes a piece of leaded glass or very heavy glass. And then the light passes through another polarizer at P, and you can look at whether the light makes it through. Here's the important point that he recognizes, is that if you have crossed polarizers, so if, let's say, the light coming into the glass is polarized horizontally, and the other polarizer at point P is polarized vertically, then those are crossed polarizers and one should not see any light. But here's the important experiment that Faraday did. He noticed that if you suddenly magnetize the glass, you apply a strong magnetic field, suddenly you are able to see the light passing through the cross polarizers. In other words, polarized light becomes rotated. That is, the plane of polarization becomes rotated when passing through a magnetic field. And the degree of magnetization alters the degree to which it's rotated. This is called Faraday rotation. It's not what it was called at the time, but has come to be known as Faraday rotation. And this is something that Michael Faraday discovered, and it's important because in at least Faraday's mind, it produced a link between electricity and magnetism and light. You might remember that before this time, electricity and magnetism were seen as one phenomenon, and light was seen as vibrations of the ether on the other hand. And what this did is it kind of brought these together and said, well, maybe light has something to do with electricity and magnetism especially. And what's going to happen is this is going to lead to, over the next several years, what's called the electromagnetic theory of light. We'll be exploring that over the next couple of weeks. Okay, so tell you what, why don't we stop there? We're going to finish the chapter 23. Next time we'll talk about chapter 24 and Tyndall's discussion of light scattering.